So today we'll discuss the structure questions related to thermal physics. A cyclist compete in a bicycle race. Before the race, the bicycle tire contained air at a temperature of 22 degrees centigrade and the pressure 5.52 into 10 to the power 5 Pascal. By the end of the race, the pressure of the air in the tire has risen to 5.6 into 10 to the power 5 Pascal. Calculate the temperature. So how we can calculate the temperature? We can use here the pressure law, because according to pressure law, pressure and temperature are directly proportional to each other. Or we can also use the formula PV is equals to NKT, where P is the pressure, V is the volume, N is the number of the particle, K is a constant, and T is a temperature. So for this solution for this question, what we should be our assumption? We should assume that number of the particle and the volume does not change. So we have the formula PV is equals to NKT, or PV is equals to nRT is there, or we can also say NKT, where N is the number of the particles. So pressure and temperature are changing, so we can say pressure divided by temperature is equals to N, the number of the particle K, the Boltzmann constant, divided by V. So these all are constant, so the ratio of the pressure and temperature should be constant. So if the first pressure is P1, the first temperature will be T1, but temperature should be in Kelvin, so we will add 273, so 273 plus 22, so it will be 295 Kelvin. And the new pressure, that is P2, so the ratio of the pressure and temperature should be constant, so we can also say P1 over T1 equals P2 divided by T2, because all these other factors are constant. So P1 is the first pressure, which is 5.52 into 10 raised to power 5. T1 is the first temperature, that is 22 degree centigrade. So it will be 295 Kelvin. P2 is the second pressure, which is given in the question, 5.6 into 10 to the power 5. Divided by the temperature T2, we don't know. When we simplify, we are finding that T2, the final temperature, which will come out as 299 Kelvin, or we can convert into degree centigrade, subtract 273, so it will come out around 26 degree centigrade. Is it clear, this question, the first part, that how we work out? Then in the second part, during the race, a small amount of air escaped from the tire. Explain how the value of the temperature calculated in the first part would be affected if some of the air is allowed to escape or some of the air escaped. So again, we'll use the same concept, that we have the formula PV is equals to NKT. So in the beginning, we assume volume is constant, number of the particles. So when you check this what is the relation, like how temperature is related with others? So PV divided by NK is equals to T. So with the number of the particle and temperature, they are inversely proportional. So 1 over N is proportional to T, or T is inversely proportional to N. So as the number of the particles like decreases, a few particles are there, for the same pressure, the temperature must increase. So temperature of the air would be higher for the same pressure. Like if the pressure is maintained, then if the number of the particle decreases, the temperature of the container should be higher to keep the same pressure. In this question, explain why the pressure exerted by the air in the tire increases as the temperature increase. And your answer should include the reference to molecular momentum as well as the kinetic energy. So we should include that why the pressure increases as the temperature increase, and that should be in terms or reference to the momentum as well. So basically what happened, as there is an increase in temperature, the molecule will move faster, the average kinetic energy of the molecule increases. So there will be greater change in momentum, because as the molecule collide, they bounce back more often. So there will be a greater change in momentum, and the ratio of the collision of a molecule with the wall of the tire increases, or rate of change in momentum also increases. So they will exert more force and it increases the pressure. So we'll write the first thing, increase in temperature will increase the kinetic energy of the particle. That is one thing. So due to the increase in temperature, there will be an increase in kinetic energy. The second thing, the particles will change the momentum often, and they will hit the wall harder, exert more force on the wall, which increase the force on unit area, or we can also say pressure. So basically when we increase the temperature, particle move faster, their kinetic energy will increase. As the kinetic energy increases, because the particles are moving faster, so there will be a there will be a greater rate of change in momentum, and as the rate of change of momentum increases, the force which the particle are exerting on the wall of the container will increase, and as a result of this increase in force, the pressure will also rise, or pressure will increase. So another question related to thermal physics, air can be considered to be an ideal gas. So if we consider air to be ideal gas, it means we assume that the force between the particles is negligible, and particles have zero size, and their collisions are perfectly elastic. So in the first part, a sample of air is contained. A sample of air is contained in a volume of 2 into 10 power minus 3 meter cube. The pressure of the air is 1.35 into 10 power 5 Pascal, and the temperature is 295 Kelvin. Calculate the number of the molecules of sample in the sample of air. So the formula to get the number of the particles or molecule, that the general gas equation, PV is equals to NKT. PV is equals to nRT or NKT. That is the same, like, because you have the equation PV is equals to nRT, where n is the number of the moles, which is number of the particle divided by Avogadro's constant. So PV is equals to number of moles divided by number of particle divided by Avogadro's constant into RT, and this R divided by Na is K. That's why we can say PV is equals to nKT, where P is the pressure, that is 1.35 into 5 Pascal, multiplied by volume, which is 2 into 10 to the power minus 3. N is the number of the particle which we are finding. K is the Boltzmann constant, that is 1.38 into 10 to the power minus 23. And the temperature is 295 Kelvin. So we need, the N is a subject here, we need N, so all the factors here, 1.3 into 10 to the power minus 23, 1.38 into 10 to the power minus 23 into 295 is multiplied. Other side it will be divided, so we'll get the value for N, the number of the particle, which will come out 6.63 into 10 to the power 22. So this is how we work out the number of the particles present in the sample. What is the ideal gas? Ideal gas means the gas which obey the gas laws, like Boyle's law, that pressure and volume are inversely proportional, Charles' law, that volume is directly proportional to temperature, and pressure law, that pressure and temperature are directly proportional, that's constant volume. So the gas which follow or obey these laws is known as the ideal gas, because real gases contradict with these laws at certain point. So ideal gas means the gas which obey these laws, all the conditions. So whenever like these laws are there, gas laws, they are only applicable for ideal gases, or it can be applicable for real gas, but at certain condition. Not all the conditions the real gases obey the gas laws. So a fixed mass of air has initial temperature of 12. The internal energy of air is double. Calculate the final temperature. So how we can work out the final temperature? Internal energy is what? Internal energy is basically a sum of kinetic and potential energy. So the temperature is 12 degrees centigrade. Which we should have in Kelvin. So what we'll do, we'll add 273. So this will be 285 Kelvin. And the internal energy is equals to sum of kinetic energy plus the potential energy. So the internal energy is equals to sum of kinetic, like when we add all the kinetic energy and all the potential energy. In the question, they say internal energy is doubled. So how the internal energy can be double? So it means either kinetic energy increase double and potential does not change. And this is what is really happened. Like for we assume at the potential energy of these gases is not changing. The only change of internal energy is due to kinetic energy. This is our assumption. So if the internal energy is double, kinetic does not change. The only thing potential does not change. The only thing what happen is the kinetic energy doubled. So, or we can also say the internal energy of the ideal gases is equals to number of the particles of the gas, in greater the number of the particle, greater the internal energy, and multiplied by the kinetic energy. So if we double the kinetic, the internal energy will be double. If we double the number of the particle, the internal energy will be double. So in short, we can say that as the internal energy is double, it means kinetic energy is double. And what is the relation between kinetic energy and temperature? They are directly proportional. So if the kinetic energy is doubled, so the temperature should also be doubled. But keep in mind, temperature in Kelvin will be double. So if it is 285, the original is 285, then how much should be the final? So double of 285, it will be 570 Kelvin. So the temperature as the temperature double, the internal energy, the kinetic energy will be double, or the internal energy will also be double.